Thanks for joining me for another video on limits. This time we will be looking at a few more rules that will help us calculate limits. In this video, we're going to look at something called the squeeze theorem. It's also known as the sandwich theorem or the pinching theorem. And as we look at examples, you'll understand why these names. These theorems are meant to help us when we have more complicated functions that we can't separate out into pieces because we might be running into problems like dividing by zero or so on. So let's look at the theorems first. And these are theorems that can be proven if we look at limits as a more formal construct. But here we're just going to present the theorems. We won't prove them. And later on, when we look at the more formal definition of limits, you'll see how we can prove all these theorems. But in the meantime, let's look at this first theorem, which says that if we have two functions, f of x and g of x, and if we know that f of x is less or equal to g of x when x is near a, okay, so a is a special point, then the limits of both functions exist as x approaches a, then the limit of f of x is less or equal to the limit of g of x. And again, when we're looking at x, it has to be close to a, but it does not have to include a because we're looking at the limit, not at the value of the function at a. So we could have a discontinuity or some other issue at a, but if these limits exist, and if in the vicinity of a, f is less than g, then the limit of f is less or equal to the limit of g as well. So that is our first theorem, and then we can generalize this basically to a theorem for more than two functions, and then we're going to introduce the squeeze theorem, which is correct for three functions. We have g of x, f of x, and h of x, and they have these relationship between their values in the vicinity of a specific point a. And again, it does not have to include a specifically, but in that area, if we can always say that g is less or equal to f and f is less or equal to h, and if the small one g and the large one h both have limits and they are equal to L, so they have the same limit at the point A, then we can deduce that the limit of f of x at that point A is also L. So, and again, they have to have this this relationship only in the vicinity of A, as close as we want to get to A, but it doesn't have to hold exactly at A. We could have a discontinuity or some other problem. Then this theorem holds. And here you have a little example. We have this purple function here, which would be our f of x. The purple function is between the black function, which is lower, and the green function, which has a higher value, all in the area of a equals 0. And you see here an inset. This is really close to 0. You see how the functions behave. Well, if we know the green limit, and it equals the black limit at a, then we can deduce the purple limit to be the same. And you can understand why it's called the squeeze theorem. These two functions, the black and the green, are squeezing the purple one into its limit at 0. I also understand why it's called pinch or sandwich. So these are the theorems, and we're going to look at two examples that show us why these theorems are useful, why it is useful to use the squeeze theorem for certain functions. So the first example uses a trigonometric function, and this is kind of typical. Since trigonometric functions oscillate, right, the sine and the cosine, they always oscillate. It could be difficult to find limits, right, because the oscillation can become quite intense, as you see in this example here. So in this example, we have the three functions. Two are the limiting functions. So we have h of x here, which is negative x squared. We have the black function here, which is just x squared. And these two functions are limiting this middle function here, f of x equals x squared times sine of 1 over x. And we might want to ask ourselves the question, what is the limit as x goes to 0 of x squared sine 1 over x? So this is our f of x. And this is a difficult one to calculate because we may want to use the rule that we found in an earlier video where we said we look at the product of a function. If we're looking at the limit of a product of two functions, which we have here, we have x squared and sine. So we can look at the product of the individual functions. And so we would like to write that this equals the limit of x squared times the limit of the sine of 1 over x. However, the limit of the sine of 1 over x does not exist. And so we really are not allowed to do this. This is not correct. So what can we do? Well, in this case, we would like to try to see if we can use our squeeze theorem because we know that we have these two functions that are limiting our function. So how did we get to these functions? So again, let's look at our first function, f of x equals x squared times sine of 1 over x. Now we know what the problem here is. It's sine of 1 over x. Let's look at that a little bit more carefully. So when we have the sine of a variable or of a function, there is one thing we know about the sine function. It oscillates, but it doesn't just oscillate to any number. It is limited. Remember, it is limited by -1 and +1. The sine of pi over 2 is +1. The sine of 3 pi over 2 is -1. And we never get a value that is larger than 1 or less than -1. So let's write out this inequality. Sine of 1 over x we know is larger or equal to -1, and it's smaller or equal to +1. Okay, so this already shows us that we have some kind of squeezing that we can maybe try to do. Now, between the sine of 1 over x and our f of x, we still have a difference in that we have to multiply it by x squared. So let's multiply this inequality by x squared. When we multiply an inequality, we have to multiply every term in the inequality. So on the left here we'll have -x squared less or equal to x squared sine of 1 over x less or equal to +x squared. X squared is larger or equal to 0, so we are allowed to multiply without changing the direction of the inequalities. So now we have this new inequality, and again we're allowed to multiply by x squared even though we're getting close to 0 because we're not actually at x equals 0. So we're looking at the vicinity of x equals 0, but not quite at x equals 0. Okay, so now that we have this new inequality, let's give our functions names. So this again is f of x. This is going to be h of x, and this is g of x. So we have our sandwich theorem, right? Again, we have it just similar to what we have right here. Okay, so now we can use this to calculate our limit. Why can we do that? Well, if we look at the limit as x goes to 0 of g of x, that's the limit of x squared, right? So that goes directly to 0. The limit x goes to 0 of h of x is equal to negative x squared, also goes to 0 as we take x to 0. So our limit L is equal to 0. So now we can say that the limit of x squared sine 1 over x is equal to, as x goes to 0, it's equal to this same limit that is the limit of g of x and of a of x. It's exactly 0. So you can see here how useful the squeeze theorem is. We were looking at a function that we couldn't use other rules to calculate the limit, right? We could not separate the x squared from the sine of 1 over x because we did not have a limit for sine over x. We got around this by using the squeeze theorem to basically pinch the value of the limit to the point where we could evaluate it. So this is a very typical example of using the squeeze theorem. Our next example is a little bit less typical, but just as useful. Okay, so our next example is going to be the function x squared natural log of the absolute value of x. So that's going to be our f of x. And again, we're going to be looking at the limit when x goes to 0, where again we have a problem with the natural logarithm when we get close to 0. As a reminder, I'll draw the function if this is x, and this is going to be the natural log of x. Well, at 1, we're at 0. The function goes to infinity kind of slowly, but it goes up that way. And then as we go closer and closer to 0, it becomes more and more negative, and it's actually going down here to sort of going towards negative infinity, while here it's going towards positive infinity. So that is the function. So obviously, if we're going to look at the limit of f of x as we take x to 0, we again cannot look at it as the limit of x squared times the limit of the natural log of x, because we do not have this limit here at x equals to 0. So we're not allowed to do this. This is not allowed. Okay, so what can we do? Well, again, we would like to look at, to try to use the squeeze theorem. I'm going to write out our function again. Our f of x is just x squared natural log of the absolute value of x. And the reason I'm using the absolute value is I want to look at 0, and I don't want to have to worry about looking at negative numbers, because we know that we can't evaluate the log of a negative number. So that's why we'll keep it with the absolute value. And so if we're looking at the limit as we take x to 0, we have a problem. So again, let's look at the natural log. Again, we're going to look at the absolute value. The natural log of x when x is close to 0, so we know that x, the absolute value, is probably much smaller than 1. The natural log is negative. So let's look at negative natural log. So we're looking at a positive number. I'll draw this. Basically, we're looking at this function now that is reversed. So 1, here it's positive. And actually, for x's that are larger than 1, it's negative. Okay, and we're looking at the vicinity of x equals 0. So when we look at the natural log of x, what we would like to find is near 0 a function that has values that are smaller consistently, and a function that has values that are larger. So what can we look at? Well, the natural log of x, the negative of that, is always smaller than 1 over the absolute value of x. So when we look at the 1 over x, we're looking at a much faster moving function as it approaches 0. It becomes larger and larger in a faster way than the natural log does. On the other hand, the natural log is always larger than the absolute value of x when we're looking at small x's, because this function is actually going to 0 as we approach 0, right? So we know that this function, the negative of the natural log of x, is always less than 1 over absolute value of x and is larger than the absolute value of x when the absolute value is less than 1. Okay, which is the area we're looking at. What is the next step? Well, let's multiply the whole thing, the whole inequality, by x squared. When we multiply by x squared, we get absolute value x squared is less or than negative x squared natural log of absolute value of x is less than x squared divided by absolute value of x. Okay, we can simplify what's happening on the left. On the left, we have just absolute value cubed, right, of x cubed is less than negative absolute value x squared, natural log of x of absolute value of x is less than, again, absolute value of x, because x squared is positive. So we've kept ourselves sort of in the positive by using a squared there and using the absolute values. Okay, now that we have this inequality, let's use the squeeze theorem, right? So because we can squeeze our f of x, which is what we have right here, between these two functions. What is the limit of the absolute value of x cubed as x goes to 0? It's just 0. What is the limit of the absolute value of x as we take x to 0? It is 0. So we can deduce that the limit as we take x to 0 of negative x squared natural log of absolute value of x is just 0. Now we can use one of our rules, multiplying two functions. We can multiply by -1 both sides, and we know that the limit as x goes to 0 of x squared natural log of x, absolute value of x, equals to 0. And so again, this is a really helpful use of the squeeze theorem, where we're not able to separate a more complicated function into its elements because the individual limits did not exist. But by using the squeeze theorem, we could still find out what the overall limit of the function is at this more complicated spot. So thanks for joining me again, and I look forward to the next video.